steady leadership of the United States and our global coalition. To see the video, check out the DoD News YouTube page, and for more on Secretary Carter's travels, go to defense.gov.
From the Fox Sports Studios in Los Angeles, here's Eddie Garcia.
Baseball, it was a battle of the top two teams in the league. The St. Louis Cardinals, best team in the National League, were hosting the Kansas City Royals, the best team in the American League. It came down to a home run.
High fly ball to right field. This was going back at the track. You can get that one goodbye. Matt Carpenter with the home run, a two-run job, and the Cardinals now lead 4-2.
Gamble X Cardinals Radio Network on the call. Matt Carpenter's two-run homer was the difference in the Cardinals' 4-3 win over the Royals. The Dodgers blanked the Mets 3-0 behind Clayton Kershaw's complete Game 3-hit shutout. He now has a scoreless inning streak of 29 straight. Twins over the Angels 3-0. That snaps the Angels' 7-game winning streak, while the Astros walk off with a 5-4 win over the Red Sox on a Jose Altuve solo homer in the ninth. Boston has lost 8 in a row. College football, Ohio State senior quarterback Braxton Miller, who missed all of last year's national championship season due to an injury, is reportedly moving to wide receiver.
Just when we think we've gone too far, we're just getting started. AFM The Eagle, serving America's best.
I thought that I've been hurt before, but no one's ever left me quite this sore. Your words cut deeper than a knife.
Yes cells. Now these cells would carry the gene defect of the parent, and through homologous recombination, one can quite readily perform gene correction. We demonstrated in this experiment that the gene repair stem cells could generate a cloned mouse which had an entirely intact immune system. But in a proof of principle, we then differentiated these into hematopoietic stem cells and grafted the mouse and restored partial immune function. It was partial circa 2002. We're now in a position where we can effect complete hematopoietic engraftment from mouse embryonic or induced pluripotent stem cells. But we're still limited because we are required to genetically modify these cells to drive engraftment. And one of the great goals of our lab, and I would embrace for the community, is to learn how to direct the formation of hematopoietic stem cells in a completely genetically predicted manner, both from mouse and human pluripotent derivatives. Now, our hope in the early part of the last decade was that we could effect the same kind of proof of principle using human cells and human nuclear transfer. But indeed, this has never been successful, in part because human oocytes are in short supply, but I think in large part because this is a very cumbersome and challenging strategy. I don't think it was ever a practical alternative for modeling a large number of diseases. I think our hope all along was that it would teach us the principles of reprogramming in such a way that we could get to the more direct and facile method of direct reprogramming. And this was, in fact, the substance of my original application as an NIH Pioneer Award grantee. And during the time that we were attempting to effect reprogramming of spermatogonial stem cells, which are really unipotent stem cells, quite closely aligned with the pluripotent brethren, the work of Shinjyuku came forward and really revolutionized the field. Now, what Shinya had realized was that there were a small set of genes among the many hundreds that are specific to the embryonic stem cell that confer this property of pluripotency, the ability of this cell to maintain a naive epigenome in such a way that it could give rise to various tissues under different conditions. And he winnowed from a large set of candidates a highly selected mini library which could be delivered en masse as a retroviral screen. And with titers such that essentially would affect the expression of any combination of those 24 factors. And he introduced these into an embryonic fibroblast, which was a fortuitous choice because these are the easiest cells to reprogram. And he engineered in that fibroblast a reporter system which allowed him to select for ES-like cells. And then in another brilliant embodiment of this experiment, it was reproduced 24 times, leaving a single candidate out in each bin, such that the 4 bins which failed identified the essential genes, which when brought together in this reprogramming experiment were alone sufficient to drive pluripotency. And these now famous genes, OCT4, SOX2, KLF4, and MYC, have since been modified. You can do it with NANOG, you can do it with LIN28, you can substitute LMYC for NMYC, you can substitute the SOX family members. There are cocktails now which can drive this reprogramming. Now, with refinements from Shinya's lab as well as that of Konrad Hucketlinger and Rudolf Janisch, we were able to produce bona fide pluripotent cells which satisfy the functional criteria of embryonic stem cells. That is, they can primerize the mouse embryo, generate contribution to all tissues, and be transferred through the germline. And then with this publication, which was in late 2006, it then became clear that we had to test whether these factors were sufficient to induce pluripotency in human cells. And indeed, it's a testimony to the robustness of this platform that just a little more than a year later, there were 3 groups that reproduced direct human somatic cell reprogramming. And then very quickly thereafter, this spread to, I would say, dozens of groups. So today, we have improved technology approaches to reprogramming. Whereas most groups have used dermal fibroblasts from a skin biopsy, a number of groups, our own included, has recently published that from a simple 10 cc venipuncture sample that can be drawn in any office, you can directly reprogram from the mononuclear cells of blood and generate a patient-specific iPS cell. So early on, we did this in a proof of concept to generate a repository of disease-specific lines, and just our initial production included the classical ADA immune deficiency, which is well-studied here and used in gene therapy, Gaucher's, models of muscular dystrophy, chromosomal abnormalities like Down's, genetically more complex conditions like Parkinson's and diabetes, and this list is increasing at Harvard and internationally. At Harvard, we've established the Harvard Stem Cell Institute IPS Core Laboratory. My colleagues Doug Melton, Jack Cowan, Konrad Hucketlinger, Kevin Egan, and others are contributing to this core. There's been an enormous appetite in the scientific community for using these cells. It's been distributed to, I believe, now almost 200 different laboratories. So what I'd like to do is illustrate a couple of examples of how we're using these stem cells to have a fresh approach to time-honored questions. Here's the work of Kevin Egan and colleagues, where he's taken a patient with Lou Gehrig's disease, generated patient-specific iPS cells, and then demonstrated using techniques that have been pioneered by work from Tom Dessel and Victor Leander, the directed differentiation into both motor neurons and glia. And there's a tremendous biology that's grown up around the work of Cleveland and Maniatis and Goldstein and Egan and others that suggests that there's 2 processes that work here in ALS. There's both a homicidal tendency on the part of the motor neurons to not survive, but interestingly, there's also, a suicidal tendency. There's this homicidal tendency of the glia to liberate toxic factors which affect accelerated motor neuron death. And working with Lee Rubin, Kevin's group is now configuring drug screens that would antagonize this toxic factor, but also improve the survival of the motor neurons directly. And these types of strategies that one would anticipate harnessing the value of these patient-specific iPS cells in the drug discovery program. We have collaborated with Sandra Rione's group. Sandra recently moved from Children's Hospital in Boston to Children's Hospital in Philadelphia. But we generated iPS cells from individuals with Down syndrome. They carry the trisomy 21. Sandra's work has been asking a question about this fascinating observation in individuals with Down, that even though they have a childhood predisposition to certain leukemias, they tend to have a reduced lifetime incidence of solid tumors. She's related this to the restrictions on neoangiogenesis in individuals with Downs, and she's reproduced that in a mouse model that carries the Down syndrome critical region 1 gene. This is a protein that acts as a negative regulator of complement-mediated angiogenic signaling. And what we did together with Sandra was to create tumors, teratomas, from normal individual iPS cells as well as those from individuals with Down syndrome, and then demonstrate by quantitative assessment of the microvascular density that the Down's tumors could not support the same degree of new vessel growth, providing perhaps substantiation of her observation that attempts to explain why there might be reduced solid tumor formation in Down